Any questions about this? Okay, so this isn't the slide, we only have like 3 slides. But this way back, a while back, this is actually kind of what you guys did in lab. So one of the things you want to be able to know on for your exam is what a titration curve looks like. So along the x-axis is volume of titrant, and along the y-axis is pH. Okay, so this was, now I hope this makes sense, because you guys are going to do some curves today that you're going to hand in on Wednesday, or you'll do them Wednesday, to hand on Wednesday. Anyway, notice that this actually is, we have the analyte, and I'll say beaker. Okay, the analyte's what's in the beaker. Okay, the titrant is what is in the burette. Okay, so this probably makes sense. What's in the beaker is an acid, so not so surprising, it has a very low pH. We drip base into it, not so surprising, the pH is ultimately going to go back after the equivalence point. So one of the things about lab is we said that the equivalence point is kind of halfway kind of symmetrical in that inflection point. Okay, so that actually is a strong acid and strong base. Strong acid being titrated with a strong base. And you can tell because it's kind of got that nice distinct shape to it. So this is a different sort of S-curve. How is this different? Well, right off the bat, you can see it doesn't start out at a low pH. It starts out with a high pH. Actually, in this case, the titrant and the analyte have been reversed. So what's in your beaker is your base. Okay, this is in your beaker. Okay, starts out basic. No pun intended. Okay, but other than that, it's still a titration curve. Okay, along the x-axis we have volume of acid being dripped in. Okay, and along the y-axis we have pH. All right. So we talked about polyprotic acids, and those are ones that can kick off acids that can donate more than once. Like H2SO4 is polyprotic, but only the first hydrogen comes off. The first proton is strong, and then the second one has a... Phosphoric acid is not one of your 3 strong acids. Actually, it has 3 hydrogens that can be kicked off. So you can see we actually have 2 equivalence points then. So one last thing to talk about is this idea of picking your pH. So when you guys did your titrations last Thursday, you guys noticed that with your second titration, when you had your weak acid, acetic acid, actually your inflection point was over here. It had the same volume, but you could see it was actually at a different pH. Your equivalence point, your inflection point of your titration curve is that's equal to your equivalence point. Wherever your equivalence point is with regard to pH, then you want to come to the chart like this to pick out your appropriate color indicator if you're going with a color indicator. So these are visual things. In Chem 1, we used phenolphthalein. Let's just find phenolphthalein on there. I love to say phenolphthalein. It's a good choice if you are going to, well, actually, if you're looking at a strong acid, strong base, you would expect it to change colors. Your equivalence point is going to be neutral. So pH about 7. And phenolphthalein is looking more like it changes pH about 8.5. So if you have an equivalence point that is, for instance, going to happen around pH 4, you come down here. So maybe a good indicator would be methyl orange. See how that works? So you're going to actually, for the 1745, question number 45, you're going to be referring to this chart. Okay, so let's take a look at 45, because that's the only thing that's going to be due on Wednesday. I was looking at it and I was like, well, how hard could this be? And I'm like, oh, there are quite a few things to do. Question 45 looks at two titrations, okay? And you're supposed to draw the curve, the titration curve that would go along with these. Titration A and titration B. Anytime you see the word with, actually, that is what's in your burette. So we have a strong acid, HI is a strong acid, and HCl are both strong acids. That's in our burette. Notice that we're going to, in our beaker, the first case have 25 milliliter aliquot of 0.1 molar KOH. In the second case, 10 milliliter aliquot of 1 molar ammonia. So that's kind of how that goes. Notice that what they want you to do are several things in sketching these curves. Come back here. There you are. And this actually is good. What I would do for both of these is to write the equation of what's going on, and then kind of what I've done in Chem 1 and Chem 2 here more recently is I write under the species what I know about it. Like I said, we have strong base and a strong acid reacting to each other with each other. Your titration curve will have an abrupt slope, like it did with your hydrochloric acid and your sodium hydroxide. But notice that the pH is going to start basic because you have potassium hydroxide in your beaker. Okay, we have an inflection point. So what this says is you're supposed to come up with your equivalence point. Okay, actually your equivalence point will be the amount of HI you need to drop in. That's a Chem 1 problem right there. The other thing, Chem 2, we talked about pH. The initial pH of your 0.1 molar solution, you can knock that out, right? You can get however you want to do it. Get the pH of a 0.100 molar hydroxide solution. That will be your initial point there. So I think that's about it. Oh yeah, the other thing, the last thing it says is pick an indicator near the pH that your equivalence point will occur at. And remember we said anytime you have a strong acid and a strong base like this, your equivalence point is going to be a pH neutral. So you got that one, right? So that's how you're going to sketch your curve with a handful of points. Okay, so for B, it's a little bit different. Okay, we have ammonia, which is a weak base, and hydrochloric acid, which is a strong acid. Again, your ammonia is going to be in your beaker. Your HCl is going to be in your burette. The thing that's different about this is that at the equivalence point, remember we talked about at the equivalence point, all of this is going to be used up. And what's going to drive the pH is the NH4+. So basically, no pun intended, what you're going to do, it's going to involve an ice table. But anytime you have a weak base like that, reacting with a strong acid, at the equivalence point, NH4+ is entirely been converted from your NH3 has entirely been converted to your NH4+. So this is where you need to figure out the molarity of that, okay, and recognize that NH4+ now is its own little weak acid. Isn't it not adorable? And here is the equilibrium for it behaving as a weak acid. Remember that actually, even though there's no Ka for NH4, there is a Kb for NH, and there's no Ka for NH4+, there is a Kb for NH3. So NH4+, no, I was right the first time. NH3, H+, NH4+. Okay, so your ice table from here. So that's your hint there. It is a very good to probably do to get you ready for the test. All right. So like I was saying, I'm gonna figure, I'm going to finish up today by doing a Unit 4 review. I'm usually not much into reviews, but I decided that I'm going to hold off and start Unit 5 on Wednesday. So here's what that looks like. And I'll go ahead and push this out there. You might recognize these terms. I don't want to be that busy at first. If you look at the end of the notes, you have that lecture guide. So all I did, and I'm thinking, well, that's a good idea. All I did is that I took that lecture guide and I chopped it up into 10 topics. I think there's 10. So for instance, the first topic, we talked about the definition of an acid and base. And we're sticking with Bronsted definition. An acid will accept a proton and a base will donate a proton. Then we talked about relative strengths of acids and bases. We said that especially a weak acid will donate a proton to a certain extent and will look like this. And then I went ahead on this slide and kind of identified the conjugate acid-base pairs on either side of the equilibrium arrow. We said we can write a Ka expression, your ionization constant for your weak acid. Okay, you're going to want to be able to know what that looks like. So the higher the Ka value, the greater the extent that it ionizes. It means it's a stronger acid. We could do a similar thing with a weak base. One thing I didn't do, and I think I'll add it to this slide and push it out there. Here at the bottom, I am going to go ahead and say, I would suggest you look up, or at least be familiar with, if you don't already know, those strong acids. I would kind of have an idea of what the strong acids are, because there's like 6 of them, I want to say. Yeah. Then we talked about auto-ionization. Of course, auto-ionization can be thought of as taking 2 water molecules and donating a proton, or we can think of it as 1 water molecule kind of falling apart. That's auto-ionization of water. The Kw for water is basically that equilibrium, and that's the hydrogen ion concentration times the hydroxide ion concentration. Kw is a value to memorize. If you're going with 4 sig figs, it's 1.008. Going with 2 sig figs, it's 1.0. Both times 10 to the minus 14, that's at 25 degrees Celsius. Then also we talked about, well, kind of related to that. If it's 25 degrees Celsius, if you know either the H plus or the OH minus, you can find the other one. You guys did a bunch of homework like that. Then kind of along this timeline in this unit, we talked about pHs, or the P function. pH is the negative log of the hydrogen ion. pOH is the negative log of the hydroxide ion. pKa is the negative log of the Ka. Then we talked about if you have the pH and you want the hydrogen ion concentration, you take 10 raised to the negative pH. If you want the hydroxide, you take 10 raised to the negative pOH. If you want the Ka, you take 10 raised to the negative pKa. Then we said that actually pH plus pOH is equal to pKw, which at 25 degrees Celsius, pKw is 14.00. So that can come in helpful. So those were all kind of things we talked about. Solving equilibrium systems, if you have a weak acid, so that's kind of what we had over here. We had actually this weak acid, and if we want to solve the system for what the hydrogen ion concentration is, here's what you got to do. I guess I won't do review sessions anymore. One is you got to write the equilibrium like this. Okay, then you write the Ka expression. Then you come up with an ice table, and you solve for equilibrium concentrations, probably the hydrogen ion or the hydroxide ion. pH in polyprotic acids, like we just saw with phosphoric acid, it's possible where an acid can kick out more than 1 hydrogen. The first ionization is the strongest, and then actually it's the one that kind of drives the pH the most, but they can be accumulative. After your first ionization, you do have a certain amount of hydrogen ion already there. So that's going to involve, we talked about one of those in class, that would be an ice table because of the common ion effect. Conjugate acid-base pairs differ by a proton on either side of the reaction arrow or equilibrium arrow. And there's this cool relationship. If they are conjugate acid-base pairs, that Ka times Kb is equal to Kw, and I've seen you guys use that in your homework. In acid-base reactions, there will always be a pair or two sets of conjugate acid-base pairs on either side of the reaction arrow. There's 4 different acid-base titration or reactions, titrations. One is where they're both strong, and one is where one is weak. And remember that if you're before the equivalence point and you're talking about a titration between a strong acid and a weak base, or a weak acid and a strong base, if you're before the equivalence point, you're going to basically have created a buffered solution. To find the pH, you're going to have to use the Henderson-Hasselbalch equation. If you're at the equivalence point for this sort of titration, okay, then know that it's kind of like we had here. If you're at the equivalence point, then what you have basically is a solution of the conjugate, whether that's a conjugate acid from a weak base or if it's a conjugate base from a weak acid. In that case, you're going to end up preparing an ice diagram. The last one is weak acid and weak base, and we're not concerning ourselves with that. Almost done. 2 more pages. So buffered solutions, the Henderson-Hasselbalch equation you're going to want to remember, and that is only for buffered solutions. So remember, there with the log, that ratio, you can either go molar concentration of base and acid or the moles of base and acid. And then I went ahead and wrote that alternate form, which can kind of be helpful. The ratio of, if they're conjugate acid-base pairs in the same solution, the ratio of base to acid is equal to 10 raised to the pH minus the pKa. And then, what else did I say? There's 2 ways to make a buffered solution with a pair, a conjugate acid-base pair. One is to simply mix the 2 together, and that would make a good question on your test, wouldn't it? And the other one is kind of what we see with titrating when you have a strong acid or base that's titrating a weak base or acid. In that case, basically, you have converted, before the equivalence point, you've made a buffered solution. Okay, you've converted part of your stuff to its conjugate. Okay, so that's another way. And last but not least, this is like problem 45 that's going to be due on Wednesday. Be kind of familiar with acid-base titration curves. This is an acid being titrated with a base. I kind of tried to make the slope kind of like you saw with your acetic acid, not as abrupt. But be able to know the equivalence point. That orange part right here that got kind of written over by pH indicators, this right here, remember we talked about the half neutralization volume of a weak acid with a strong base? So basically, you see whatever volume this is, you split it in 2, and right there, if you go up and pick off the pH, that pH is equal to the pKa of that weak acid. I just think that is so cool. And then last but not least, it kind of goes back to that figure. Oh, I didn't do too much. Let's see, what should I say here? Picking an indicator. So basically, you have that table where it has pHs across here, and then you have your indicators here. So basically what you do is, for instance, if you want a pH 3, you go down here and you see which pH will change in that at pH, which indicator, excuse me, see which indicator will change about pH 3. So that's kind of how you do that. All right, so I'll push those out there, and that's all I have today. So like I said, Wednesday, be ready for Unit 5. It's chaos, I tell you. No, really, it is. Entropy and that sort of thing.